Okay, I thought we'd go through some additional materials. We've gone through independent samples, t-tests, ANOVAs, things of that nature. And so that covers correlations, regressions. That covers a lot of the statistical tests that you'll do in psychological science. There are some other tests out there, though, that you might use, and we'll cover a couple just to get you a little bit familiar with them, the chi-squares. And then also, there was some students that actually asked me to cover a couple of other things, including the idea of p-hacking, where you're basically trying to make the data tell the story that you want it to tell instead of it just being, an objective, here's the data. I love this quote. It's from one of the videos that I have a link for here in just a second, but the idea that you're going to torture the data until it confesses. This is not how we're supposed to do things. What you should do is you come up with a plan, how many people you're going to run, what analysis you're going to conduct, and then do it. And if it doesn't work, it doesn't work. And, that's fine. Things you don't always get a significant result, but the idea that you're trying to force getting a significant result, that's not ethical. Anyways, I do like that idea, the torturing the data. I'm not going to play these videos because I don't want these videos on top of my video. I don't know how YouTube would react to that. But in any case, these are some really good videos that I found on the idea of using statistics to prove what you're trying to prove, which again is not what we're trying to do. We're trying to, as scientists, we're trying to find the truth. No, we're not trying to, just necessarily support our ideas, use the data to support the ideas that we already have. And then some videos on the replication crisis. And I do think that if you get a chance, you should watch these videos. And I've also I posted some of these articles and thoughts in the course materials if you want to look. There was one study when I was a graduate student by BIM, the idea that people could essentially, his data showed that people could see into the future. And it's like, well, no, not really. And so what it really showed was the idea that maybe how we do stats is maybe not the best. And the idea that you can find things if you, force it to a certain degree. So if you get a chance, you should look over those videos. And I did again. I posted some articles in there in the modules. I also posted some. So we had the replication crisis. At the same time as it's starting up, we have the BIM article come out that people can see in the future. It's not true. And then with replication crisis, people, myself included, we were trying to replicate experiments from other labs, and it just wasn't working for whatever reason. And part of it, again, is probably related to how we were doing the stats. It was probably related a lot to, we've talked about sample size. And so if you get a sample size of 15 and you get a significant finding, if you had ran, 150, maybe that you wouldn't have that significant finding because that p-value will go up and down the more participants you get. In any case, the mini labs projects, they came along, and I think they did 4 or 5 different, where they tried to do these large scale replications with many different labs, trying to replicate some of these findings that we've talked a lot about, the really exciting type findings that we see in psychological science. And they were showing basically that they weren't able to replicate those things. There's also a website, it's a blog that you can look at here, Data Colida. You can go there, and what they're trying to do is that if they see new articles come out and they're like, something's wrong with this, they'll try to pinpoint whatever maybe p-hacking type things that they tried to do in those articles. And they've discovered, some findings and tried to get some things overturned. Just with any of these things, just be careful and mindful. I mean, some people, I don't believe this, but there are some people that consider them to be doing a witch hunt and that they're the replication police, that they're just trying to go out and to sabotage careers. I don't necessarily think that that's the intent, but I can see why maybe some people would think that that's what they're doing. If I had some work out there and people looked at the stats and they're like, you're wrong, you faked it or whatever, that would be discouraging. But so just be careful and mindful that that there are many different opinions out there. Also, and I do want to make sure that everybody understands this, the p-hacking is not always malicious. So there are some people that do things with the stats, and that's just how they were taught, and they don't realize that it's not the right way to do it and potentially is unethical. So again, it's the p-hacking and things of that nature. It's not always malicious. For example, you may see in an article, you'll see p equals 0.000. The reason that the researcher is saying p equals 0.00 is because that's what the output table said in whatever statistical analysis or whatever statistical program they were using. So maybe SPSS on its output, it says mine, I don't know, I have mine set up differently, so it'll just say it's less than 0.001. Mine does not say 0.000 because you cannot ever have a p-value of 0. If you have a p-value of 0, what you're saying is there's no chance that you're wrong, and that's not what we do. With that null hypothesis testing, we never really accept the alternative hypothesis. What we do is, either fail to reject or we retain the null hypothesis, but we don't really accept the alternative. We can provide evidence that supports it, and we can be 95% sure, or 99 or 99.9, but we're never going to be 100% sure that this finding is completely the objective 100% truth. So if you see, and you will, some of you, when you do your presentations, you will see in their paper, they'll have p equals 0.000. When they do that, again, they're not being malicious. They just don't understand precisely what they're doing. They should say p less than 0.001 to say that there's still that 0.1% chance that the null hypothesis is true. If you see it like this, p less than 0.000, which you will see that sometimes too, it's like this is not even a possible. This is like you saying that you're 101% sure. It's like it's not possible. So p cannot be equal to 0, and it definitely cannot be less than 0. But again, they're not being malicious. They just don't know. Now, that being said, sometimes it is malicious. So like what Elizabeth Holmes did with Theranos and the idea that they had these tests and they had all this data. It was just smoke and mirrors, fabrication. And they were doing it, I assume the main reason was to make money. There are some other examples of scientific fraud. So what Theranos did, that is malicious. It is fraud. There are some examples out there, and you can look at this one if you want. What I think happens with some researchers, some scientists, is they get an idea in their head that this is what the data should show. And that also they need the data to kind of show that to keep their career going on the trajectory that they want it to go on. And so they need to have the idea of publish or perish, that you have to publish these articles to make sure your career stays on that trajectory. And if you don't, maybe you don't get to keep your job. So sometimes people will publish these things with either the p-hacking or sometimes just straight up falsified data to keep their job, but also the idea that I think some of them think it's like, I know that this is what the data should show, and just my sample didn't quite show it like that, but I'm going to tweak it just a little bit because I'm positive that my thoughts, my hypotheses are true. And again, that's not how a true scientist would think about this. Everybody's wrong all the time. So it's like, if your hypothesis, the data does not support your hypothesis, it just doesn't. And so you don't want to get too married to how the ideas that you think that the data should show. So in any case, it's not always malicious. Sometimes it is, and sometimes it's kind of complicated. They're doing it to keep their job, and they're just certain that their hypotheses are true when maybe they're not. In any case, I mentioned the term p-hacking now a few different times. So what exactly is it? It's basically where you are trying to get the data to tell some story that it necessarily doesn't say. The different types of p-hacking. One, the stopping rules. This idea that before you do your research, you should do what's called a power analysis to see how big your sample size should be. And if the sample size says, you need 50 in group 1 and 50 in group 2, you go with that. And once you get to that sample size of 100, you're done. And then you run the analysis, and whatever it shows, it shows. What some people do is they'll run 10 participants, and then they'll run the analysis. And then they'll run 20 participants, and then they'll run the analysis. And maybe it starts to drop down. That p-value starts to drop down. They're like, ooh, we're at a p.10. And so they run 10 more. Now they've run 30 people. And now it dips below, p dips below 0.05. And they're like, okay, we're done. We got our significant finding. We're done. That's not how it works. Again, you decide the sample size before you run the experiment. And if you do it like that, run it until you get the significant finding. That is what's called stopping rules. And you should have those rules set up to stop at a certain number and not the number that gets you significance. And also, it's like if you get to that significant finding, it's possible it could go back up. If you ran 10 more, maybe now it goes back up to p is 0.10. So the idea of doing that is another version of chicanery that they'll do. Outliers. There are definitely some cases where you're going to have some legitimate outliers, and you may need to take those out of the analysis. If you do take outliers out, though, you need to make sure that, like in a footnote or somewhere in that results section, you say, we took this one person out. They were an outlier. This is maybe an explanation for that outlier, and why you took him out. Some people would say that that's actually the outlier is the interesting one, possibly. I do know, but though sometimes you're just going to have some bad data that gets in there. For example, I used to run some research that was based on reaction times. And so you'd have to look at the computer screen and you'd have to press, I don't remember what it was, I think J and F. And so like you press F if it was this thing, you'd press J if it was this. And so you're pressing the back and forth button. You have to really focus and think, and it's about the reaction time and all that. I'm going through my data and I had one data point. And the numbers were way off. It didn't make any sense. One, there was a lot of errors, and two, the numbers were way too low. The reaction time was way too low. And I was like, what is going on here? And I talked to the person that was actually ran that participant, and they said, oh, that makes sense. Because they said what they saw, they looked in there to see while they were doing the experiment, and they weren't even looking at the screen. They were just tapping the buttons. They were looking all over the place. And so that's bad data. And that's not useful. Our sample, we want our sample to represent the population, the humanity, what we think was really going on out there psychologically. And the idea that somebody's doing this, that's not useful data. So I took that person out and I made a note of it in the results. It's like we had to remove this one person. So all that being said, you may have outliers and there may be legitimate reason that you would want to exclude them. In other cases, maybe not. So it's kind of, it's up to you. However, if you're going to take them out, you do need to let us know that you took them out. Variable manipulation, there's all different kinds of ways that you can do this. For example, let's say you run it as maybe as a regression. You're running these continuous variables and your regression's not significant. So you're like, okay, well, I'll do what's called a median split, where you'll take it and divide it into high and low. And so now you have two different groups, a high group and a low group, and you'll run like a t-test to compare those two groups to each other, and that's significant. It's like, okay. But originally, if you were going to run them as continuous variables and you were going to do it as a regression, you're like, well, it's not significant. And so you take it and you have to cut them in half and to do these other groups. That's probably not the right way to do it. Definitely not. I mean, you should, have that plan beforehand. Some people have to maybe transform their data. And for sometimes that transformation is legitimate. Sometimes maybe not. And they're just doing it so that they can get that significant finding. Excessive hypothesis testing and multiple comparisons. We've talked about this, the idea of alpha inflation. I did post a Bonferroni calculator here for you to look at, but I can tell you quickly what it is. If you run one test, you're going to set your alpha at 0.05, and you're just going to do one comparison. That 0.05 stays at 0.05. If you run two comparisons, though, your chance, at 0.05, we're saying there's a 1 in 20 chance that we're going to be, wrong, that if we get that p less than 0.05, there's 1 in 20 chance that it's actually a false positive. So that is going to happen. You will get false positives. But if you run more comparisons, you get what's called alpha inflation, where the 0.05 goes up each time you're doing that. So instead of 1 in 20, now we're 2 in 20, 3 in 20, however. And so with the Bonferroni, and some people say it's a little bit too conservative, maybe not, but what it does is it cuts that alpha in half. So if you set your alpha at 0.05, but then you run two comparisons, your alpha is now going to be at 0.025. If you run three comparisons, it cuts that in half, and now you're at 0.0, whatever it is, 125. So the Bonferroni is reducing your chances of having that alpha inflation. So if you do 5, 6, 7, if you think about that, if you're going to do like 10 comparisons, it's going to take your alpha way down from that original 0.05. So it's definitely something you want to think about when you're designing your experiments. You don't want to just throw everything in there, because then you're going to have to do these corrections for the alpha inflation. Because again, if you have 20 variables in there, you do 20 comparisons, one of them within the realm of possibility of being a false positive. It's selective reporting. It's kind of a similar thing. And I do have an example for this here. So let's say we are looking at depression scores. So what we're going to do is try to do an intervention for depression. And we don't know what we're doing. And so we just decide to throw a bunch of variables in there and see what happens. So we have a control group that we're not going to do anything to. And then we're going to compare a group that we have them listen to heavy metal. And then we'll have a group that we're going to have them watch YouTube videos. We have a group that we're going to have them eat Pop-Tarts. And then we have a group that we're going to have them play hacky sack. And we're going to see if those things reduce depression. Again, we're just kind of throwing things in there because we don't have a good hypothesis, because it's an example of what things that people might do. In any case, so if we look at this data here, we would run a one-way ANOVA because we have one independent variable. There's 5 different levels: the control, the heavy metal, etc. So analyze, compare means, one-way ANOVA. We're going to move our OG data to the dependent list and our OG group to the factor. We got our effect sizes. We'll go ahead and do our post hocks just to show you for education purposes, the LSD, the Bonferroni, the Tukey's, options, descriptives, and I like to get the mean plots. Continue. Okay, let's look at this. So we get our means first. Control group has a mean depression score of 2.998. The other group's really close, 3.02, so on and so forth. We look at our ANOVA, not significant. So our F was a 1.2. That should be the end of this. It's not significant. If we look through here and we go to the multiple comparisons, the LSD is when we don't do any adjustment for alpha inflation. And if we look there, control to hacky sack, there is a difference that actually is significant. So what we're saying is that hacky sack, their depression scores were 0.054 less than the control group, and that difference is significant. Regardless of everything else we're going to do here, is that difference meaningful? It's significant, 0.05, but is that actually meaningful? So if we look here at this, the descriptives, again, we're talking about comparing a 3.052 to a 2.998. And so while that difference may be significant, is it meaningful? Probably not. If we're talking on a scale from 1 to 7, that is a tiny, tiny difference. In any case, so that LSD, not making any adjustment for the alpha inflation, does give us a significant value. The control to hacky with the Tukey's does not, 0.22. And then for the Bonferroni, which again is going to just chop it in half each time, the control to a hacky sack, the p-value is about a 0.4. That's a huge difference there. So between making no correction and making the Bonferroni, we went from a 0.04 to a 0.40. But let's say if you're not a scrupulous person and you run this data and you get that back and you see, oh, well, if we just compared the control to the hacky, we're going to get that. What you could do, you shouldn't do this. So I feel a little bit weird about showing you how to do the things the wrong way, but it's useful. If we the heavy metal, the YouTube, the Pop-Tarts. Well, I guess one reason I'm telling you this example is that they did this with, and you could watch it in one of the videos, the idea that people got younger by listening to certain songs. Clearly, that's not something that can happen in reality, but one of the things they did was they cut out some of the groups. So let's just say we're like, forget it. The heavy metal, the YouTube, the Pop-Tarts, we're just not even going to talk about them, and we're just going to look at the control to the hacky sack. And so now we don't even have to do an ANOVA. We just do an independent samples t-test. We're going to move our p-hacking group to the grouping variable, define groups 1 and 2, and then we'll move our p-hacking pH data to the test variable. Click OK, and then ta-da, our essentially a 3 to a 3.05 actually is significantly different. We get a t-value of a 3.08 degrees of freedom. One tail or two tail is significant. Again, is it a meaningful difference? No. And also, the way that we've done this is unethical. And so that's one way of doing selective reporting, that you don't report all of the groups that you had. And so how can you avoid this? We've touched upon these things before. One, have a clear research plan from the get-go. You wouldn't throw in let's eat Pop-Tarts to reduce depression. That would be silly. So you'd want to have a good, clear research plan that's elegant, that uses the least amount possible to try to find what you're looking for. And so yeah, you'll have good, strong hypotheses. You will do the power analysis. You'll find out what your sample sizes need to be. Once you reach that point, you'll stop collecting data. You'll run the analyses that you've already said that you were going to run before you even started collecting data, and then go with that. And it's like, if it's significant, great. If it's not, something's wrong with the hypotheses, or something's wrong with how you ran it. You wouldn't want to try to manipulate that to make it significant. Another way that you can do this is the idea of pre-registering these. There's different websites you can go to do this, basically where you're like, this is our research plan, this is our hypotheses, these are our variables, These are how many people we're going to run. These are the statistical analyses that we're going to do. And then also the transparent reporting. At least now for you, you know the idea that the stopping rules is not something that you should do. I mean, some of these things that I'm talking about here, at least not stopping rules, it wasn't really something that I remember talking about when I was like an undergraduate or maybe even a graduate student. I don't really recall. In any case, you do know about them now. So the idea that you would not do some of those things that would go along with this transparent reporting. On kind of a side note though, I wouldn't get too lost in the idea of, there's so many different ways that you can manipulate the data. Does that mean that psych science is even real? It's not just in psych science, it's in all fields of science. They all had the same replication issues. So it's not perfect, I guess is how I want to put that. And just to be mindful of that, it's like, okay, there are maybe some problems with how we do it, and it's not perfect, but it is what we have, and so we will go with that. Some people will get kind of lost in some of these things, and it becomes really hard for them to either conduct research or to believe anything from any psych science paper. I've had professors in the past that got a little bit too deep into these rabbit holes, and it affected them. In my opinion, I think it affected them negatively. So yeah, just be mindful of these things, but don't get too lost in the minutia of some of those concepts from a mental health point of view. Okay, so that's the p-hacking. We're going to now talk a little bit about the chi-square. We've got two of them that we're going to talk about. First one is the chi-square. This x2, that's the chi-square. With one variable, it's called the goodness of fit. And so what we're going to do is have one single qualitative variable to see if it's, and it'll make sense here in a second when you see the example, if it goes along with our expected or hypothesized values. Again, it is one single qualitative variable. We've been talking about this entire semester. Usually most of the stuff has been quantitative, where we're looking at numbers, and we're looking at numbers as far as like on a continuous scale. But for example, and this is from our textbook, if we were to look at blood types, we would have, so blood type would be our one qualitative variable, and we have 4 levels to that: O, A, B, and AB. And if we know the general population, if we know those observed values or the expected values, so like if 44% of people are O and 41 are A and 10% are B and 5% are AB, that would be our expected values. And then we could run a sample to see if our sample is congruent with those expected values or if there's something different, weird, strange about our sample. So let's say we collect the blood types of 100 students. For O, we get 38, which is kind of close. A, 38 to 41, kind of. B, 20 compared to 10. So we got quite a few more maybe in B than we expected, 4 and 5. So we will go to SPSS now. So here we have that blood type, those frequencies that we just discussed. If you want to, so that variable view, I just entered these in. So 1 is an O, 2 is an A, 3 is B, 4 is AB. If we take off those value labels, you can see that. We are really dealing, we're telling the SPSS numbers, but we do have those value labels for us. So yeah, and we have our frequencies. What we have to do first is we have to weight the data. So we're going to have to tell SPSS about the frequencies for these types. And how we'll do that is go to data, weight cases, and we'll move frequency, select weight cases by, we'll take frequency, we'll move it over here to frequency of the variable, and then click OK. And now it's basically telling SPSS, when we talk about these blood types, when we do the chi-square, that we're using these frequencies. To actually do the chi-square, go to Analyze, and it's a non-parametric test. We're going to go to the Legacy Dialogues, and then we'll go down here to chi-square. We're going to move our blood type over. And then what we need to do is put in those expected values. And if I recall, they were 44, 41, 10, 5. And so now essentially what we are going to be doing is comparing that 38 to the 44, that 38 to the 41, 20 to 10, and 4 to 5. Technically, we need to have 5 in each group, but and it'll give us an error message. Click OK. And so yeah, our expected was a 44, our observed was 38. It gives us the mean the difference there of 6. This is our actual test statistic. Our chi-square is an 11.24. What we would do next is go to one of our figures that we all love to do, All the instructions I just went through are on these pages. We would go to table D and look at our critical values of chi-square. And so how we're going to get our degrees of freedom is going to be categories minus 1. And so we had 4. We had O, A, B, so on and so forth. So 4 minus 1, one of those mathematically wouldn't be free to deviate. So we have, those are our degrees of freedom. So we go to 3, and if we want to do 0.05, we need to get a chi-square value of 7.81, which we did get. Ours is an 11.24. It is greater than 7.81. So ta-da, we do have a significant finding. So something is, different about our sample compared to what we expected it to be. That's one qualitative variable. It's the goodness of fit. The second one we'll talk about is a chi-square with 2 variables. It's called a test of independence. So we're going to be looking at the observed frequencies on 2 qualitative variables. Another example from the book. If we are looking at the idea of people, if you found a letter, would you actually, try to get that letter to the right person? So the idea of returned letters. And let's say you lose these letters in 3 different locations, 3 different neighborhoods, downtown, suburbia, and campus. So returned letters has 2 levels, yes and no. Neighborhood has 3 levels, downtown, suburbia, and campus. It's like, is there a difference between these locations on like the percentage of letters that are returned? And we would expect, our total is 200. So whatever 200 is divided by each one of these. If we had 6 different ones, 200, somewhere around 33. So we would expect there to be about 33 in each one of these. And it's like here on campus, I don't know if that's gonna hold out there. In any case, we would go to, I have these set up in SPSS already. These are, and you can go in and put in those value labels, but it was 1s and 2s and 1, 2, 3, 1, 2, 3. Returned yes for 1, no is 2, and then downtown's 1, suburbia is 2, campus is 3. And then those frequencies. The first thing we got to do again is weight those cases. So weight cases, reset it, and we're going to now move over frequency 2 to the weight cases by. Click OK. And then we're going to go to Analyze Descriptives Crosstabs. And we're going to put, let's see, if you think back, returned was the rows and neighborhood columns. And we're going to go to our statistics and get our chi-squared. Okay, ta-da, we have an N of 200. This looks exactly like it does on that figure from our textbook. And then down here we have our chi-squared test. And this one, it does tell us that it's significant, p less than 0.001. If we wanted to, we could look it up again. It's the same. Here's the instructions if you want to go through those. So yes, our values of 14.02 to get the degrees of freedom for this one. We're going to take columns -1, rows -1, and take those times each other. So we had, for the neighborhood, we had 3 different ones. So 3 minus 1 is 2. For the returned, it was 2. So 2 minus 1 is 1. 2 times 1 is going to be 2. So our degrees of freedom, 0.05, we need to get about a 6. And we got a 14. So, and also, SPSS said that our P was less than 0.001. And if you look over here, the critical value for 0.001 and degrees of freedom 2 is 13.82. And so we just barely exceeded that critical value. So we could put P less than 0.001, not 0.000. That's the chi-squared, short, dirty version for it, for the test of independence and the goodness of fit. A couple other things that next semester I'll probably talk about when we go through each analysis, but the idea of assumptions, there are some things you want to look at before you start doing your statistical analyses. And one, the outliers, to see if there are some data points that maybe stick out that maybe shouldn't be included. This is one of our examples from the independent samples t-test where we were comparing EPO. We know EPO increases endurance. I think we were doing it for a group of depressed people. EPO, it's kind of like the blood doping, and these were what people got in trouble for. There were the bicyclists that got in trouble. There's also been some people in like the UFC that have done EPO, and it's a banned substance because it does increase endurance. We did do our independent samples t-test here. If we wanted to, we might look to see if we have any outliers. As far as how you want to decide if you have an outlier or not, there's a million different ways to do that too. Again, some subjectivity with stats. In any case, what we could do is just get the z-scores. However, let me show you first. If we go to descriptive, so analyze descriptive statistics, descriptives, all we do is move over our DV endurance over and click that Save Standardized Values. However, we get our z-scores, the standardized values. What we talked about before, the idea that if a number is 2 standard deviations away, maybe it's an outlier. And we do have one that's 2 away. However, we need to look at each group individually. So you don't put all of your data in at once like I just did. So we'll clear that one. What we're going to do, there's probably several different ways to do this, but one way that I used to do was select cases. So we go down to, sorry, let me do that again, data, select cases, and then we'll move over. We're just going to look at group 1 first. So we move group 2, and we click if these conditions are satisfied. Group 2, move it over. If group 2 equals 1, we'll do that first, and then just click continue. Okay. So now it's only showing the 1s, the 2s are gone. We have that filter right there. Anyways, we can do it now. Descriptives, descriptive statistics, descriptives, move over our endurance variable, save standardized values. And if we go back, now it's not a significant. So that 18, yeah, it's big, but and it has a z-score of a 1.65, which, yeah, it is pretty big, but it's not over that 2. So it's when we separate those groups out, it's not an outlier. That's one thing to consider, your outliers, but if you do it, you do need to go group by group. Another thing we want to look at is normality. So, we talked a lot about standard distributions, normal distributions, and we're kind of making an assumption when we're doing our stats, looking at our data, that we're kind of assuming that it is on a normal distribution. There are also many ways to look at this, but one way to look to see if your data is distributed normally is to do this statistic. So now I have all of my data back. Clear that out. So just group 1 or group 2. We did the outliers for group 1. You'd also go through group 2 and check for outliers there. So we will do, analyze, descriptives, and explore. We're going to move group 2 over to factor list, and we'll move endurance over to the dependent list. There's a whole bunch of things we could look at. Outliers, all that stuff. The one I want to look at is this normality plots with tests. Again, there's other things you can go through and look at if you wanted to, but you're going to get quite a bit of information, the mean, median, mode, minimum, maximum, all those things. This is what we're looking for right there. I have it here in the PowerPoint. If this significance was below 0.05, then our data has violated the tests of normality. Maybe they're skewed, maybe they have the kurtosis, something's off if they were below 0.05. And if they are, there would be, some people would say you need to run a different test if you don't have a normal distribution with your data, because if these tests were designed for normal distributions. In this case, we don't have to worry about it because it is normal or normal enough, normal-ish. There's the assumptions, the outliers, if you want to look through that. If some of these assumptions are violated, such as it's not a normal distribution, maybe a different test should be conducted. For example, independent samples t-test, instead of running that test, you would run the Mann-Whitney. And then also there's different tests for each one of these. I just wanted to make you aware of that you want to make sure that, you don't have outliers, that your distribution has somewhat normal. And if it's not, some people would say you do need to run a different test. So just something to keep in mind. That being said, it's like, we can't get people not to put p is less than 0.000. So I don't know if a lot of people are actually doing these other tests, if they're aware or not. But technically, yeah, you should probably be running a different test. Okay. I hope that was useful and helpful, and that you can use that maybe in your future. Thank you very much for listening.